Hello, my name is Michael Morgan. I'm a doctoral candidate in the combined psychology program on counseling and school psychology at Florida State University. And it is my honor to be giving this presentation in the special track on knowledge and cognitive science and technologies in the context of the 24th Multi-Conference on Systemic Cybernetics and Informatics. I'd really like to thank my co-authors for this paper, Zach Langford and Dr. Deborah Osborne, for all of their assistance in developing this model, this presentation, and the accompanying paper. I'm really excited about this. I don't think anyone in vocational psychology has developed anything like this. It's significantly different than other models that include things like machine learning for predicting hiring and stuff like that. What we have here is a model that we believe can validate a specific theory in vocational psychology. Right now, there are a limited set of really influential vocational psychology theories. We've got the social cognitive theory, we've got constructivism, we've got chaos theory, and we've got cognitive information processing theory. And we believe that this theory can be modeled computationally, and that we can turn that computational model into an artificial narrow intelligence that can make career decisions. And it's really exciting because we think that the implementation of this particular model can also help inform cognitive architecture. It's really important. CIP theory, as it's known, as I'll be referring to it in this lecture, is the backbone of the Florida State University Career Center, which is an internationally recognized career center. Just some of the base statistics about this program: every single year they offer services to about 19,000 students. So that's career advising and counseling. 19,000 students in a school that has roughly 40,000 students. So nearly half of the university receives services from us on a yearly basis. And we're one of the few universities with a career center where graduates who attain employment within 6 months say they are able to find employment because of their interaction with the career center, instead of family and friends being the most common way that they find their employment. And that is a very uncommon thing that speaks mountains about the kind of services that we offer. And CIP theory is really one of the gears that turns this wheel that makes the Career Center work. So validating this theory in another area is something that can contribute greatly to the popularity of this theory and to helping spread it more to more countries, more universities, and really helping it grow as one of the main focuses that helps change career services in our society. So as a general overview of what we're going to talk about today, it's important that not only do I talk about career, but also how this particular process can help inform cognitive architectures as a whole. So we're going to talk about that first. I'm going to go into some more details on CIP theory, because that's really going to show you what aspects of the theory we're attempting to implement in this model. We're going to talk about the actual nuts and bolts of the model and go over a plan of implementation. We've got some ideas of how we're going to move forward next. And then we're going to come back full circle and talk about things like the significance of this particular model and some challenges that we're expecting to face. So cognitive architectures have really grown since the 1990s. They've been around since for at least the past 40 years, this idea. But if we go to a Wikipedia page on cognitive architectures now, it lists more than 40 different cognitive architectures. One of the things that's really exciting about this branch of cognitive science, of computer science, is beginning to model more closely biological systems. So for the mission statement of the BICA Society, which is the Biologically Informed Cognitive Architecture Society, has this influence at the end of it. I absolutely love it. It says, systems develop their cognitive and learning functions. So there's this emphasis not just on creating, instantiating the cognitive architecture, but developing them in such a way that they grow. And that's one of these things that we believe that this computational model can help inform because of its relationship to identity as a whole. So if we want to create a cognitive architecture that's going to model a human cognition, a human being, then we're going to need to develop a system that has a sense of self, a self-awareness, an identity in some ways. So one of the things that's really interesting about that is, well, it's incredibly complicated. There's lots of things that are going into it, and that's one of the reasons why we think that vocational psychology and this particular model can be a stepping stone to developing that. Another aspect is that identity develops. The psychosocial model of identity development was written about in the 1950s. We have about 100 years worth of research now on different strains of identity development. So one of the things we know is it emerges over time. However, there is this argument about the discovered versus the constructed nature of identity. We have sort of, on the more constructed side of things, one of my favorite psychologists is Vygotsky. It's a Russian psychologist, and he wrote about how we internalize language processing. That this idea is, as human beings, we begin learning by mirroring language, and at some point in time, we couldn't necessarily say when, but at some point in time, the sounds that we're making, the words that we're saying, we internalize that voice. And we begin to identify with the internalized voice, and it is from that that we develop this sense of self. These are my thoughts. This is what I'm thinking. This is who I am, right? And that's sort of a different approach because it builds it all in culturally. We become these amalgamation of everything that's outside gets put inside, versus sort of a discovered way of looking at things, and that would be more of a epigenetic way of looking at things, much more genetically influenced, that we have predispositions. And that what happens is, as we grow, as we gain greater knowledge of ourselves and interact with our environment, we begin to identify and validate pieces of ourselves as being ourselves. And that is where this sense of self comes from. That's the discovered way of looking at identity development. And you'll see in our model, that's more the side that we're going toward. But there's a complex interaction between those two things, and we believe that this model can represent both sides of that coin. As I said, identity development is a very, very complicated topic. But one of the pieces of core identity that's almost universally accepted is a vocational identity. During late adolescence, during what we call emerging adulthood, which takes place from roughly age 18 until the early 30s, individual really develops this sense of self. And there's these two core aspects. One of them is our relational selves. Romantic, friends, family. Who are we in relation to these other people? Another important one, though, is what role do we take in our society that gives us the opportunity to fit into society and for society to recognize us? So that vocational identity is a core aspect of our being. And it emerges in response to career exploration and career commitment. There are different ways to represent these selves. One of them right here is this PPIK trait complexes. This comes from Ackerman and Hegstad, 1997. And what it kind of says, it sort of fits with this more discovered way of looking at things, is we can associate various traits and interests that an individual has into these clusters. And then we can look at different kinds of occupations that also align with these clusters. and that an individual can make occupational choices and develop a sense of coherent identity when they discover the overlap between who they are in their cluster and a potential option that they decide, this is a good option for me. We believe that this model can do that. So I'm going to tell you a bit about cognitive information processing theory. What we have determined is that the basic framework and model of decision making in CIP has the necessary and sufficient components to be operationalized as a computational model. Something that a lot of other career theories, in fact probably no other career theory of decision making and development can do those things, because they're very ambiguous in some ways. The chaos theory of career is very ambiguous, and even though it's built on these ideas of quantum mechanics, to then take these models and apply them to the human and then develop them into a career decision-making computational model is going to be nearly impossible at the current time. But we believe that CIP is ripe for this. In CIP, this pyramid of information processing is one of the central constructs. And what we're going to be talking about is really how these two parts down at the bottom can be represented in this computational model. On the bottom left side, you see self-knowledge. So this is the idea that an individual has certain skills and values and interests and employment preferences, although we're going to leave that one out for the time being. But skills, values, and interests. And as they grow as a function of episodic knowledge, episodic memory of themselves, they develop an idea of who they are in respect to these three domains. At the same time, they engage in career exploration that involves learning about the world of work. So that's here on the right side, that's the options knowledge. And what happens over time if an individual doesn't have any barriers to the process of career decision making, something that is kind of rare, as these two sections of the pyramid build up, a natural process emerges whereby a best option is identified and selected. It can almost take place as an automatic process, and in this case, it would represent bottom-up decision-making. Now in the middle here, we've got information processing skills, and specifically in CIP, we're going to be talking about the Cassave cycle. I'm going to talk about that in the next slide. And up at the very top here, we've got metacognitions. Metacognitions in this theory act sort of like a limiter to the decision-making process, and this is one of the pieces where we believe that this model in particular has something special to offer to cognitive architectures as a whole, because if we can implement these limiting factors to the process of decision-making under ambiguous circumstances, that we can begin to model framework that we can measure whether or not it's accurately representing how metacognition influences decision-making in a human. In the Cassave cycle, it can be, as I said, both an automatic or a controlled process. It becomes controlled if there's a barrier to the decision-making process. It's really driven by this idea of career exploration, and that's where the individual experiences growth in those two bottom domains on the pyramid by interacting with their environment to gain knowledge about the world of work and about themselves for the purpose of career development. And it results in career decisions and career commitment. Importantly, as it relates to vocational identity development, it's career exploration plus career commitment. But career commitment cannot begin until a decision has been made. So with this computational model, we're representing what it takes to make the initial career decision, and that will in some ways mimic aspects of the vocational identity development process. In our model, we're really going to be focusing on these three phases of the Cassave cycle. Analysis is a phase that's really devoted to information seeking, building up those two domains at the bottom of the pyramid, although it also relates to the other aspects of the pyramid. But it's really building up both declarative as well as episodic memory to be able to facilitate this decision making. Now, at some point in time, during the knowledge accumulation process, the individual begins making linkages. There's a matching that takes place between those two bottom parts of the pyramid. And during that matching process, a certain number of options are identified that could be potential matches. And now we're getting into the synthesis section of this pyramid, where ideally an exhaustive list of potential matches would be found. But this is being done under ambiguous circumstances. There are so many potential options out there that none of them can be, not all of them can be known. So what takes place is at a certain point toward approaching the exhaustive list of options, certain options become more attractive. Certain options represent a better fit, a better match. And so a pruning process occurs and a narrowing down to about 3 to 5 options. This is one of those places where CIP theory is informed by cognitive science, in that 3 to 5 is generally accepted as the number that working memory, 3 to 5 chunks of information, working memory in a human model can compare those things simultaneously. And once we have those in working memory, we move into the valuing phase. And at this point in the valuing phase, one of those potential options, as they're getting thought about, mulled over, will emerge as a tentative first choice. These are the aspects of this model that we're hoping to implement at this time. We think we found a really interesting way to do that. Once a first choice emerges, then an individual would start making plans to implement that choice, and they would return to the communication phase, which is sort of a governor that determines, do we need to re-enter this? So ideally in the future, we would have the model represent sort of a feedback loop where it could go over and over again as necessary. It's important for us to be able to do that in the future. Metacognition, as I was saying, acts as a limiter on this entire process. And in CIP, this is one of the things that's really important for this model, to be able to identify instruments with sufficient psychometric properties that we can have the data from human samples to validate the outputs of this particular computational model. In CIP, we've got dysfunctional career thoughts, and that's measured with the career thoughts inventory. It's been used since 1996, and it's got wonderful psychometric properties. And we can see how things like commitment anxiety, for instance, is a very common construct throughout vocational anxiety, through vocational psychology, that looks at when a person gets to the point where they are going to make a decision, the amount of anticipatory anxiety of losing out on a better choice, thinking I have to make the perfect choice, it makes it so that they can't make any choice at all. And so we believe that in iterations of the development of this model, that we can implement these additional metacognitive limiters that include sort of affective components and can influence the way this process would play out. But to do that, first we have to make the model that's going to represent the process if everything's perfect. And with that, we're going to talk a bit about the actual model that we've developed. We're very excited about this model. It's a system that we believe models sort of the career exploration process and creates an optimal decision under limited and ambiguous information in some cases, because we lack perfect information of the world of work, and how it is that a single option is going to emerge over time. So essentially, with interests, values, and skills, these are the 3 domains that we want to represent. Now, all types of jobs can be represented sort of as clusters of components. Remember that PPIK model where there's different clusters of things in there? Well, 3 of the big ones are interests, values, and skills. So to get started, what we have are matrices that we are developing with a limited number of potential options of interests, values, and skills. Importantly, the matrices do not have to have the same number of interests, values, and skills across. So in general, with interests, we have commonly agreed upon that 6 main interest categories are viewed as sufficient to represent interests. But then when it comes to skills, when it comes to values, things become much more murky in ways. There are instruments that say there are 18 different core values. Some others say that there are 10 core values. With skills, do we want to represent skills as work skills? Do we want to represent skills as attitudes, aptitudes, which could be better measured with something like an intelligence test? And if we look at differences across intelligence tests, then we'll see that in some of them they're going to have different measures of intelligences. Would we want to represent that as each one of those different measures is a different facet of a skill or an aptitude in this case, maybe with something like the ASVAB? Or we could potentially use a measure of career-related skills such as clerical skills and things like that that wouldn't be represented in these. So it's important for this model to have that flexibility, and we believe that it does. Now, with the model, what we're going to do is have a limited number of each one of those sets selected and then created into a single matrix. Additionally, each one of these matrices are going to have things that associate them with others. They're going to be neighbors in a way. And on the next slide, I'm going to show you how we view this. When we put all of those matrices together, we're going to have one gigantic matrix made out of matrices, which could be sort of identified as lattice points or something like that. Given that we're only choosing 3 at this moment, we're representing them as a cube here. So each one of these would represent one matrix. On the left side here, we can represent each one of those matrices as an image with a unique topology. Now, one of the things that we're planning to do with this particular model, once we have the base 3, now we'll know what the base 3 are, but we need to make it so that it can associate with a single option as being the best fit. With all of the different occupations in existence, there are so many that if we just looked at them as constants in this case, that it would select far, far too many. And we would have to add in more and more sets to be added into the matrix, and that would add on additional layers of complexity that's going to make it beyond our capabilities at this time. So to be able to reduce that down, what we've decided to do is add weights to each one of the individual choices. So what we have here in this matrix right here, if we look at the top, each one of these alphas is going to represent one of those 6 interest categories. If we assess this with something like the self-directed search, the individual is likely to have a propensity whereby one of these interests is clearly weighted more than the others. And it is with that that we can develop sort of a classification process that associates it with individual occupations based off of the weights of those particular choices. Now, we have here sort of like the starting state. This would be a perfect sort of topological representation of what it would look like if the computer system knew all of its weights to begin with. But we're going to mask the weights from the computer system to begin with. We're going to give it a random seed, and then we're going to mask it so that this is more like what knowledge it will have. And it would say start in a specific area and begin to grow. So maybe we'll give it all of the interests, but then only one weight. We can even design it in such a way where the weights fluctuate over time. And what we're going to do is create a sequential process that will represent career exploration, and it's going to allow the system to gain more information both about its own weights as well as perfect information about the world of work while it's exploring. This is the way that we're going to do that. in the gigantic matrix, we are going to give it orders. This is the sequence by which it is going to explore, and it's going to start off in a specific sort of space of the gigantic matrix. And as it's doing that, it's going to encounter the individual lattice points, and it's going to gain, we're going to give it perfect information of the lattice points. So that's one break with the actual reality where it's not perfect information at start, but we're going to give it perfect information about the lattice points as it goes along. So it's going to be collecting different occupational matrices with the weights, and it's going to be able to compare itself in a limited fashion to some of them, but it's going to need to choose, once it gains that, which direction it's going to move in to continue exploring. So it's going to continue to accumulate information about the gigantic matrix and the weights that are associated with that in a way that's going to allow it to match its own matrix and the weights to the individual lattice points. So it's essentially a system by which the computations will allow it to place itself inside of this gigantic matrix. That's the matching process. And what we're going to have it do is we're going to have it use sort of a goodness of fit index. And we're going to change this goodness of fit index as it goes along. But every time that a certain criterion is met for a goodness of fit, it's going to take that potential match and put it off to the side to begin the next phase in our computational model. And the way that I would have you sort of visualize for yourself about this is these bubbles. Imagine, if you will, a fixed volume of space. And every single time that a criterion is met in the potential match, it's going to be like adding heat. Say heat's being added to this volume, and this begins to cause bubbles to emerge. Now, at the end of this process, if we continue to do this and bubbles are emerging in a fixed space, at some point in time, one bubble will occupy basically all of the space. And that's what this particular equation represents. We're going to have a proliferation of bubbles because the criterion's being reached. But they're going to be small, so they're not going to be occupying all the space. But as that's taking place, additional weights in the self-knowledge aspect of our exploration model is going to be refining itself. And so certain matches are going to increase in their goodness of fit, while other matches are going to be decreasing in their goodness of fit. Eventually, as these bubbles are emerging, enough of them are going to dissipate, and certain ones among them are going to begin cannibalizing or consuming the other bubbles until such a point where about 3 to 5 emerge at the end, and they will continue to prune themselves down until a single bubble remains at the end. Now, importantly, the way that we're planning to build this is that it will not need to go through the entire gigantic matrix before this process ends. And so that is one way that this model would be able to represent the career decision-making process under imperfect knowledge and ambiguous knowledge circumstances. So we're extremely excited that we believe that we have the right combination of calculations that can take a starting state without information and then provide it with certain kinds of information over time to arrive at a final decision state that would represent the ending of the valuing phase in the Cassave cycle. We do have some plans for how we're hoping to go about implementing this in a computer model, but there are some particular challenges that we're expecting to face that we have not yet fully resolved. One of those is that we are going to need a lot of data to measure the accuracy of our model as it relates to the human decision-making process. So we expect we'll need thousands of data points in our archive. Now, the Career Center at Florida State University has been acquiring data and conducting programmatic research for decades. So we have an archive. The question is going to be, does the archive have sufficient information and the necessary information for each of those participants that we could represent skills, values, and interests? Right now, we are in a process of taking our archives and digitizing it and reviewing what's in there. And so this might be one avenue that could offer us a solution to that problem. If it doesn't, though, we are also going to need to find a way to begin acquiring information in those three areas. So one of the things we'll need to do is identify what are going to be the best psychological instruments for us to measure these particular constructs. Of course, things like validity and reliability of the instruments are going to be vital for this process. And we have some pretty good ideas. I mentioned earlier the self-directed search that's used extensively at Florida State. At other universities, there's something called the strong interest inventory, and there's some theoretical overlap between these instruments that might offer us some concordance that maybe we can reduce the need to heavy lift on interest. But there's much less consistency as it relates to measuring values and skills. There are some softwares in existence right now. I can think of the SIGI and Focus 2 are some of the most common computer-assisted career guidance systems that sort of represent what we're hoping to do. But these systems present the human with assessments of interests, values, and skills in some other domains. However, it then provides you with a giant list. It usually does not whittle it down to just a single idea. So with our computational model, we believe that we can move beyond what those systems currently offer. Additionally, as it relates to measuring metacognition, there are different areas of metacognition. In the context of career decision-making, CIP has the Career Thoughts Inventory. And this is a very attractive measure of metacognition, and there really aren't many other measures of career-related metacognition, but that brings us to the idea of other aspects of metacognition that we could measure. Things like working memory abilities, things like ability to inhibit behavioral responses. These all relate to metacognition or executive processing, and so there's lots of decisions that need to be made here. Another important limiting factor is going to be the financial burden of administering thousands of CTIs or thousands of self-directed searches. So another potential option is to use the ONET online career exploration or the interest inventory, the skills inventory. And this is going to present us with another cost-benefit analysis because they're validated instruments and they're open source. But are they the best instruments for what we are hoping to accomplish? So that is going to be something that we plan to do, but we haven't done yet. We are also going to need to build our gigantic occupational classification map. So there are thousands of different occupational titles in existence, and the ONET Online, the Dictionary of Occupational Titles, and the SOC codes already sort of associate them together in different ways. Right now, one of the most common ways is a hexagon, the RIASEC hexagon that relates to those interests, as I was telling you, in the self-directed search. And one of the things is that this model relates those occupations to each other in a 2D way of organizing them. So you can organize them based off of similarities and distances between them, but we want to add in an additional axis, a z-axis, and we want to use a skills, values, and an interest sort of axis way of looking at it. And there's going to be some questions that we're going to have to answer as it relates to that process, especially given that these measures don't represent scale data. They represent ordinal data, interval data, maybe sometimes. So we're going to have to develop a system by which we are organizing them together. And even though I showed that picture of sort of a cube as the way it's represented, when we're done with this, it might represent a very different shape based off of saturations and the way we're assigning weights and things like that. So these are going to be vital aspects of the process in implementing our plan to try and get the best way of validating it and simulation of everyday life and what the process is there. We really want to use an iterative approach to this. It's such a heavy lift to try and do all of these things. We don't want to try and build in all of the metacognition and things like that to begin with. What we want to do first is build the system so that it represents the ideal decision-making process, the automaticity of the decision-making process. And then we want to add in the internal modifiers. So these are going to be things like metacognition or affective things that are influencing the process. They're already built into CIP there. And then once we've done that, we want to add in these external modifiers as well. So there are some things that in a perfect model, in the most robust and valid computational model here, it's going to be able to represent what happens after the decision's made and occupational choices made, and then things including maybe job loss for no reason. But in the organizational literature, there's also a lot of research on how an individual restarts this process because they develop job turnover intentions. And so that would be a process whereby the valuing phase is ended, a single option is chosen, then they experience in some ways a world of work, and they find over time that the fit between them and that particular option begins reducing below a goodness of fit index. And these are things that we plan to implement later. In CIP, lucky for us, we've had all the hard work done here. They have a model whereby high readiness for decision making, this is called the two-dimensional model of decision making, is based on capability and complexity. Now capability is represented as these internal modifiers, whereas complexity in general represents external modifiers. So if we were looking at this two-dimensional model, we would start down here where the process is relatively automatic, and then we are planning to move into this section where internal modifiers like metacognition limit the process. And then we would actually remove the internal modifiers, add the external modifiers, and validate this section of the two-dimensional model, and then put it all together to see if we can do all of these things together. I would like to take this time to thank Drs. Reardon, Dr. Sampson, Dr. Peterson, and Dr. Lenz. They are credited with developing CIP. They published the first articles on CIP that built up the framework in the late 80s, the early 90s. Most recently, Osborne et al. 2019, I have it in the references, published sort of an overview of CIP as a whole. I could not have developed these ideas and this model without the input of who we call the four horsemen, or horse people, I suppose, Sampson, Reardon, Peterson, and Lenz. Even though they have taken emeritus status at Florida State, they keep offices and they keep going in, they keep doing work to refine CIP. And they have a sort of an open door policy with graduate students like myself where I can just go in and talk to them about things like this model. And I am incredibly grateful for all of their feedback and helping me better understand the model and how we might be able to represent it. So finally, we're going to sort of review what we've talked about so far and talk about the significance again of what we're hoping to do. We believe that modeling identity development is a gap in the current cognitive architectures. Cognitive architectures like EPIC, like ACT-R, already have the system in place. The system can develop knowledge of the world and maybe itself in it, but the idea of helping the system develop a sense of self, an identity for itself, is something that the cognitive architectures can't currently do. Now, when looking at theory of identity development, given that vocational identity is a core aspect of that, we believe that the strong psychometrics and strong theory and things like career decision making, as it relates to the idea of discovered versus constructed identity, represents a place where maybe we can begin to chip away at that problem. We also argue that cognitive information processing theory offers the best platform to begin modeling vocational identity development, because that CIP pyramid and the Cassave cycle are designed in such a way where the important pieces are explicit and can be currently modeled in a computational system. Big challenges that we have ahead include building a data archive, because of course once we hopefully implement this system, we're going to want to be able to validate it based off of human data. Part of that problem is going to be identifying the best vocational instruments. As I said, we've got 100 years of research on vocational psychology. There are a plethora of research validated vocational psychology instruments that we would like to review and implement, but we're going to have to narrow it down at some point in time in a way that's going to offer us the greatest validity and reliability, so that what we're comparing the outputs of the model to is good instruments. We're going to have to develop that occupational information matrix. One of the problems that's going to be involved there is that it's not really scale data. There is no true zero. We're going to have to develop a plan to implement these three sets of information, skills, values, and interests associated with the thing like the Dictionary of Occupational Titles. And one of the choices we're going to have to make is how exhaustive do we want to get to begin with? There are thousands, and we're going to need to be able to transform the information there into this model. We might begin by limiting the number of occupations that we're going to have in our model to begin with to represent sort of to be a sample, a representative sample with generalizability to the full Dictionary of Occupational Titles. Then, once we have that, we're going to need to identify additional computational modifications to add process limiters like metacognition, like affect, like the external factors such as job loss, or one of the interesting ones is, say, external conflict here. This is a place where capability and complexity overlap. Commitment anxiety. This is one of the reasons why we chose the sort of bubble model of the way the idea is emerging, because, say, for instance, if we have a fixed volume and we know that we are trying to create bubbles in some ways, well, say we reach a point where we're almost at the end and all the bubbles are cannibalizing each other, and we change the total volume. Suddenly there's more volume, so there's more space for additional bubbles to emerge, and the process has to continue going beyond the necessary place. That, it might be one of the ways that we implement commitment anxiety, but we're going to have to continue to discuss this. We're going to have to build it so that it runs on its own, and then we're going to begin adding in these additional computational processes. External conflict, for example, too, might be added in as, say, a constant that is informing the goodness of fit such that no bubbles can emerge to begin with because the conditions are not appropriate. So we've got some ideas. We're really excited to continue to pursue them, but there are going to be some serious challenges to developing this model. Finally, with the significance of overall this particular model, as I started off with, we believe that if we can implement this model, that it would offer one of the strongest possible theoretical validations of a career development theory to date. No other model of career development is capable of implementation in a computational model such as this. What's really also important, what's really also exciting about CIP theory as the model that we're using to build this is the explicit inclusion of metacognition in the model. And this, again, from the Bika Society, we have sort of a way of looking at the level of cognitive architecture, the sophistication of the cognitive architecture. And you can see way up at the very top, we have metacognition and self-awareness. And the argument here being that if we can implement a computational model of career decision-making, of vocational identity development, that we can begin to simulate this process of identity development overall. And as a artificially narrow intelligence, then this could be a module, for instance, that could be added into systems such as EPIC, such as ACT-R or SOAR in a way that can add a really interesting way of building on our understanding of human development and the mind overall. Again, I want to thank you for following me on this journey through this presentation. I've had a lot of fun. I've had a lot of fun building this presentation. I've had a lot of fun creating this computational model. I'm really excited. It's a cutting-edge way of looking at career decision-making, and it would not have been possible without the WMSCI conference and the KCST special track. And I really want to express my deep gratitude to my second and my third author, Zach Langford and Dr. Deborah Osborne, for helping me with this process. And finally, I'd like to thank Dr. Reardon, Dr. Sampson, Dr. Peterson, and all of the reviewers that gave me great feedback on the original paper submission. Thank you all so much. My name is Michael Morgan, and it has been a pleasure to talk to you today.